about remorse, revealing a hidden sequence to speed up monadic reflection. So if I was in the audience now, I would go, what? So let's start with something really simple, right? Because I think everyone should be able to understand this, or most of it at least. So, lists and list concatenation. And we're going to talk about a performance problem here. So this is the standard definition of lists and list concatenation. So concatenation means plug them together, right, depending. Hopefully this is familiar to everyone. Otherwise I think I've prepared the wrong talk. So what is the problem here? Well, the problem is, so here we have it's either empty or it's a head and the tail construction, and if we want to concatenate two, well, if the left-hand side is empty, then it's just the right-hand side, and if it's a head and a tail, and then we say it's the same head, and we recurse over the tail, right? Okay. So what is the performance problem? Is that it depends on how you place the brackets, whether it's fast or slow. Really? Yes. Let's see. Okay, let's do this one, right? So the top one is fast, and the bottom one is slow. So let's see. Let's start evaluating. It doesn't matter in which order, so I'm just taking the one that is easiest to visualize. So let's take that one first. We select it, we traverse it to the end, and we plug on the second list at the end. So this costs us traversing a length of list 3, like list of length 3. And then we select that one, and we do the thing again, and we're done, right? So this costs us 2 times the list of length 3. If we do this one, it's actually more expensive. Okay, let's see. We traverse that one, we're done, and then we select the big one, right? So this is different than before. This one is length 6. So this costs us traversing in total 9 nodes. So, summary. Top one fast, bottom one slow. Okay, so and of course if you make a big expression, then, so if you associate your expression like this, so I've drawn the tree here, and this O plus should be plus plus, right? So then this one is really fast, and this one is really, really slow. This is a turtle, it's a bit dark maybe. This is a turtle, it's a cheetah, I think. Maybe it's a leopard. I don't know. This one is actually quadratically slower than the left one. So, there is actually already a solution to this. It's called continuation passing style. So, how does that work? Now we have 2 types. Before we had just 1 type, the list type. Right, but now we have 2 types, namely a build type and an observation type. The observation type is just the list type. The build type is something with functions. Doesn't really matter what exactly. For the purposes of this talk, actually it's this, but it's a bit confusing, I think. So how does that work? Why does this solve the problem? If you use this build type for concatenating, then it doesn't matter how you associate, right? It doesn't matter how you place the brackets. So both the left one and the right one are fast. But there is another problem. Namely, if you start alternating between building and observing. So you have this build type, and at some point you want to pattern match on the result of concatenating, right? So you want to see if it's a head and a tail, or it's empty. So then you have to convert it back, because this is a function, right? You can't actually pattern match on a function. So you have to convert it to a view type. So then you pattern match it, and then you want to do concatenation again. You want it to be fast, so you convert it back. And then you want to pattern match again, and then you do this, and if you do this a couple of times, then it's again really, really slow. So what is the solution for this? Is not to use this continuation passing style stuff anyhow. It's just to use a much better sequence data structure, such as the ones in this lovely book. And if you do that, then the whole problem goes away. So, the rest of this talk, I'm going to tell you exactly the same story again, but with different structures. Right? So now we have lists, and now we're going to see with trees and monads. But the story is mostly the same. So just that you know what's going on. So, what is the problem? For some monads, this expression is slow, and this expression is fast, but they're actually equivalent, because of the monad associativity law, right? So these two things should be exactly the same, otherwise your thing is not a monad. Of course, we also can use continuation passing style here, then it's known as the continuation monad transformer or the codensity monad transformer or something fancy. And if you then start alternating between building and observing, it's again very slow, just like with lists, right? So, does this actually happen? That you alternate between building and observing with monads? Yes, it does happen. It occurs with monadic reflection. What the hell is monadic reflection? Well, I try to explain this as simple as I can, hopefully. Suppose we have some monad, M, and it consists of sequences of actions, right? So here are n actions. Maybe the first one is print something to the screen, then read something from the input, then mutate some variable, I don't know, something. So actually it's not, this is a simplification, right? Because in reality, the actions, which actions will occur can depend on the outcome of the other actions, right? So it's a bit of simplification, but bear with me. So what is monadic reflection then is if you can sort of look inside this sequence structure, right? This sequence of actions. So suppose I have a function here called one action. It takes some monadic computation, such as this one, right? And it then gives me back a new monadic computation, which then carries a value either A or another computation. So suppose we run this on this, what it then does is it executes the first action, and it gives me back right, and then the rest of the computation, right? So this allows you to sort of look inside the monadic computation. So if there was just one action, it would execute the one action and it would give me back left and then the result. So clear? Yeah. Everybody's nodding. Okay, so does this actually occur? Yes. Actually, I have the solution to this and Olaf knew the problem, so this is typical, right? Typically how these things go, I think. So it occurs with monad logic. This is this paper by, I don't know, Olaf, Kuzeliov, and some other people. And this for really fancy logic programming monads. It occurs at iteratees, coroutines, and monadic FRP. It can occur with free monads, depending on what you're doing with them. It can also occur with extensible effects. And it does occur in the limited continuations, which is something that induces headaches. Okay, so how are we going to solve this problem? So let's first, I like simplicity, so let's first look at the simplest other structure that also has this sort of problem that it depends on how you place the brackets. Right, so let's look at this tree. It's a binary tree, which we also saw in Deutsche. Well, not exactly this one, because this has no thing at the leaves. So it's even simpler. It's even simpler than Deutsche. So it's either a node with two trees as children, or it's a leaf, and we have a substitution operator, which takes a tree and another tree and then returns a tree. So what does it do? It replaces all the leaves of the left-hand side tree with the right-hand side tree. So, how does that work? If the left-hand side tree is a leaf, then it's just the right-hand side. This looks a lot like list concatenation, right? Just a bit more general. And if the left-hand side is a node, then we recurse over both children and substitute the right-hand side tree in both children. Yes? Great. So, this has exactly the same problem. Really? Yes? So let's see. The top one again is slow, no fast, and the bottom one is slow, I think. Yeah. Let's see. Okay, we select this one. We traverse the entire tree, reach all the leaves, and then we replace it with the right-hand side. So this costs us the size of this thing, right? Then we select the left-hand side again, and this costs us this, and then we're done. Okay, now we're going to do it with the other association pattern, so that means how the brackets are placed. We select this one, the same thing, right? And then we select the big one. And then we're done. So you see this has exactly the same problem as with lists. But how are we going to solve this, right? So it's not clear to me, actually it is clear to me, but it's very confusing. You could do this with continuation passing star with 2 continuations, I think. And this is guaranteed to confuse me, at least. I don't know, if, how about you? Maybe you're really good at this. But it's not really clear how to do this while you're still able to be, while you're still able to alternate between building and observing, right? At least that's what I'm going to show you. I hope it's not sort of, oh yes, of course, yeah. So how are we going to solve this? We apply a familiar trick, namely we have 2 types, one for building and one for observing. Observing meaning pattern matching. So the view type, or the observation type, is simply the same as before, except that the children are now of the build type, right? So it's a node with 2 children which are build types, or it's a leaf. So then what is the build type? The build type is just a sequence, an efficient sequence, namely it has efficient concatenation of view types, right? So it's just a sequence of view types. And we use an efficient sequence data structure here, such that the whole thing becomes fast, right? Okay, so why is this a sequence? Well, you can think of it like this. If you have this big expression, where this is substitution, right, for trees, then this is just, the sequence is the arguments of this expression, right? So the A1, etc. are in this sequence. This is what the sequence gives you. And then it's sort of obvious that it doesn't matter how you place the brackets, right? If you do this, then this comes out, and if you do this, then this also comes out, right? So it doesn't matter how you associate, how you place the brackets. So if you use this, because we're not really doing anything yet, right? We're just placing it in a sequence. It's just fast if you do it like this, and fast if you do it like this, because the exact same sequence comes out. And so you see that these things are mutually recursively defined, right? So the view type is a node where the children are build types, and the build type is just a sequence of view types. Loop, 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 loop. So we saw that if you use this build type, then it doesn't matter how you place the brackets. So that's goal 1, right? So we solved that problem. So now we just need to be able to efficiently convert from the view type to the build type, and vice versa, right? Okay, how do we do that? Well, from the view type to the build type is actually really simple, because the build type is just a sequence of view types, right? So from the view type to the build type is just, ta-da, singleton sequence. The other direction is a bit more, so this direction is fast. The other direction works like this. So we had a build type, which is a sequence of view types. Suppose here we have some tail, right, some other elements, but the first element, the head, consists of a tree with 2 children, L and R. So what do we then do if you want to convert this to a single view type, right? So this is already a view type, but we need to do something with this T. So what we do is we push this T down to the children, right? Because this is what substitution does. It just pushes it down to the children. So here we use this efficient concatenation, right? Because if this is fast, then this whole thing is actually order 1, right? It's just one step, basically, or 2 steps. So that's how we do that. So that's also fast, right? So both directions are fast. It doesn't matter how you associate. Brilliant. Can we now apply this exact same trick to monads? And not quite. Almost. But the problem is we need efficient sequence data structures for this kind of thing, right? we have this monadic computation, and we have a number of function arguments. But the problem is these functions are all of a different type. The first one is A goes to MD, the second one is B goes to MC, and the third one is C goes to MD, etc. So let's consider something simpler again, right? Because I like simplicity, and I hope you do too. Suppose we have three functions, and f goes from integer to bool, g goes from bool to char, and z goes from char to string. And so it's obvious that we can compose these, right? So we compose these functions, and then we have a function of integer to string. Because the intermediate types are sort of erased, right? The bool and the char. We don't see them popping up here. This is they're sort of existential, right? They exist sometimes. So what we want to be able to do now is to store these things in this, instead of composing them, we want to store them in a sort of sequence data structure, right? So suppose, I'm now going to show you how you can do this with the head and the tail list. So suppose this thing is a sort of head-tail construction, and this is the empty list, but it's a function list, it's a list of functions. Then I'm going to show you how to create a data structure such that you can write this thing, and this thing has a type, function list, and the first function takes integer, and the last function produces a string. How does that work? This is where the GATs and the existentials come in, so that's a sort of connection with the previous talk. So if we have a function list that takes two arguments, namely the type which is the argument of the first function and the output of the last function. So if we have an empty function list, then it's basically sort of like the identity function, right? So it's a function list and the input type is x and the output type is the same, right? Like the identity function. And if we have a head and a tail, we have a function, goes from x to y. We have some other function list, the head and the tail, which goes from y to z, and then we now have a function list from x to z. And you see that here, the y is existential, right? It's erased in the final type. Okay, and we can generalize this a bit, such that here it takes functions, but it could be any type constructor with two arguments, right? So we can generalize this function to a type constructor with two arguments, then this pops up here, and here it really doesn't do anything. But here we see now that we get instead of a function, we just get a C with two arguments, and the rest is the same, right? Okay, so we could use this to store this in a head-tail list, right? And then, oh, really? I thought it was much less. That allows me to relax. Let's take some water. So he said 5 minutes. I thought I had like 2 minutes for this entire thing. Okay. So this allows us to put this whole thing in a head-tail list, right? So then this is a list. This. And it takes an mcon with an input type A. And so this mcon is of this type, right? So you can use this to instantiate this. For head and tail. Okay. No, so you get that, right? So, but this is just for, yo.
Is your M missing a type synonym, or is it fixed in some way?
Oh, sorry, this should be a new type.
Okay.
Yeah. So yes. This should be a new type for this to work, actually. So in the paper we say, but we don't, this looks nicer. But in reality it should be a new type. Okay, but the inside, but this is just a head-tail list, right? It's not fast at all. This is actually, this will have the exact same problem we started with, right? Because, just a head-tail, shut up. It's just a head-tail list. But of course, we can apply the exact same trick to any kind of, so this is the inside, to any kind of sequence data structure. And we call these type-aligned sequence data structures. And this type-aligned means these type is sort of threaded through, right? Like this function composition. And we have implemented this for finger trees, for all kinds of catenable queues in this thing. And it actually gives you more type safety because this existential type ensures you that if you do some operation on this and you produce a new sequence, that the order in which these elements are the same, right? If you sort of reorganize your sequence a bit, but just for performance reasons. So using this efficient type-aligned sequence data structures, if we use these efficient type-aligned sequence data structures, then we can apply the exact same trick to monads. Namely, we have a build type and a view type, and the build type is just a sequence of view types. And then we have for monads as well, that it doesn't matter if you do this or this, because they both end up being the same sequence, efficient type-aligned sequence. And we can also efficiently alternate between building and observing. Brilliant. Do you have an example of this? Yes, we do. Okay, here's the example. It's a monad logic, so it's a logic computation. 2 minutes, okay. Then I have to speed up again. Here we have an expression that's wrongly associated, right? So it's, there are 3 implementations. We have the red one, which is a sort of straightforward logic implementation, right? We have the black one, which uses spooky 2 continuations. Took me hours, days to figure out what was going on here. And we have the blue one, which is our new fancy, smancy thing that does everything right. Okay, so suppose we have a wrongly associated expression, right? Then we see that the original, so the straightforward red implementation, becomes quadratic in the input size. But the 2 continuation implementation in our new fancy smancy thing have no problems at all. But if we start alternating between building and observing, then the 2 continuation thing, how horribly complex it might be, is also quadratic, right? So this doesn't work. But the original one and our fancy smancy thing are fast. So the important thing to remember here is in both graphs, our blue new fancy smancy thing is fast, or linear in the size of it. Okay, so that was it. This was the problem. We have 2 kinds of expressions, and the left one is fast, but the right one is slow. We had already a solution for this, namely called continuation passing style. But if you then start alternating between building and observing, it's slow again. We had, I don't know what this is. Oh, we had an insight. The insight was to use these efficient sequence data structures, because it's sort of the same as the problem with lists, and to instantiate this build type and view type such that you can efficiently convert between both, right? And to do this for monads, we introduce these type-aligned sequences, such that we can do the exact same thing for monads. And if this went a bit too fast, or it was very unclear, or something else, I suggest you read this wonderful paper called Reflection Without Remorse, Revealing a Hidden Sequence to Speed Up Monadic Reflection. And also, if you want to use something, like something based on this, you can install 4 packages, 4, yes. Type-aligned, which contains type-aligned sequence data structures, Reflection Without Remorse, which contains free and operational monads, which have efficient alternating between building and observing. You have this logic T, which I sort of explained, and I suggest you don't install this package, because this is the limited continuation package. Yeah, and I made some, this is the whole thing again, which is totally understandable only for me, I think, but okay. That was it.
Time for one question that sheds a bit more light on this subject, please.
I have a question. I had already heard about this, and it can do some things that code density transformation can't.
Yes.
So now my question is there anything code density can do that this can't? So does this obsolete code density, or? Well,
so if you're not alternating, well, there is nothing that code density can do that this can't. But, if you're not building, alternating between building and observing, then it's probably codensity is faster. So that's it.
By constant factor, or?
Yes, constant factor. Yes. This is because asymptotically it's as fast, and it depends on the sequence data structure. So.
Okay, thank you very much.
Yep.